Okay, so last time we talked about representations, and we're going to talk a bit more about representations today. So let's just recall what that means. So a representation of a C-star algebra is what we mean by that is representing it as bounded operators on a Hilbert space. So for that, we need a Hilbert space. And a star homomorphism. So the star homomorphism, of course, is into the C-star algebra B of H. And we still said that whenever this map is injective, that this representation is said to be faithful. And then we saw that every C-star algebra has a universal representation, which is always faithful. And the way we constructed that was by taking the direct sum of all the GNS representations of states on A. So this was, remember, where n phi was this kernel. And pi u was the corresponding sum of the pi phi's, and these were just extending multiplication on the left. So and then extending it to the whole Hilbert space. Okay, so now we're going to see some more about representations. And we'll see later in the course that in general, having representations of a star algebra is a nice way to construct C-star algebras, particular things like group C-star algebras and cross products and group void C-star algebras. But I'll leave that stuff to Tristan. So first of all, we have what's called, so we've already seen the universal representation. We saw the GNS representation of a state or a functional. And we also have something called a cyclic representation. So if we have a representation, So if we have a vector psi in H, we call it cyclic. If the linear span of the set pi a applied to psi, which we'll denote by pi a psi, is dense in H. So a vector is cyclic if its orbit under these operators is dense. And if such a cyclic vector exists, then we call the representation itself a cyclic representation. Okay, so the obvious question one might have is one of these representations we get from the GNS construction, so built from a state or a positive linear functional, will this be cyclic? And indeed it is. So we have the following theorem. So from any positive linear functional on our C-star algebra A, we can make the GNS construction. And it will be cyclic. And its cyclic vector will satisfy the following. So it will be the unique vector satisfying. Okay, so pi phi a, we want to apply this to our cyclic vector, and then we can take the inner product with the cyclic vector. And what does that give us? That just gives us phi applied to a. And moreover, if phi happens to be a state, so phi itself has norm 1, then so does this cyclic vector. Okay. So the proof goes like this. So just to make notation a little bit nicer for A and A, I'm going to let psi A be this A plus N phi, which is in H phi, and such guys, of course, are dense. Now let's have an approximate unit. So bounded and increasing and positive. Okay, then we can look at the associated vectors in H phi, and note that if lambda is smaller than mu, we have the following. So we can look at the distance between psi u mu and psi u lambda. Well, by definition of the inner product here, that's just going to be phi applied to u mu minus mu lambda star, but of course these are positive. And so then the same thing again. And since these u mu u lambdas are at most 1, we see that this is less, and then phi is positive, we get that this is less than u mu minus u lambda. And we know that this sequence phi applied to an approximate unit, this is going to be increasing with increasing and bounded, and we know it converges, and in particular converges to the norm of phi. So this tells us that these xi's, xi, u mu's, u lambdas, this is a Cauchy sequence. And so it has to converge to something, which we will call psi phi. Converge to something which we're calling psi phi. We don't actually know what it is necessarily yet. Okay, so now let A and A, we want to show that this is a cyclic vector for our representation. So for any A and A, we know that the map from A to H phi, which takes something x to psi x, is this map is continuous. So we have that pi phi of A so this is just by definition of our psi phi. And we know that pi phi A, this just acts as multiplication. So we get and remember that these psi lambdas, that's really just, so we're multiplying A here, and now this is a limit, and this is an approximate unit. So we're getting, this is going to be A plus n phi, which is just psi A. And these psi A's, as we noted at the beginning, these are dense in the Hilbert space. So we see that pi phi A is dense. So this is indeed our cyclic vector, as we were hoping. And now we need to check this second claim, that this is the unique vector satisfying this condition here. And then if phi is a state, then this vector has norm 1. So let's check that. Now, this is a star representation, so this is actually just pi phi A star times pi phi A. So we can move the pi phi A star across. And then take its adjoint, so we get pi phi A. And we just saw above that this is just psi A. Psi A. And then by definition of this inner product, that's phi of A star A. Now, that means that our picture here holds for positive elements, since every positive element is of the form A star A, and we know that the positive elements span our C-star algebra. So that means that we get the result for all elements. Okay, so now we got to show that so suppose now that phi is a state. So by 4.1.8, we saw that phi always has a unique extension, norm preserving extension to the unitization. So we can assume that A is unital. So that means that the norm of phi is exactly phi applied to the unit. So clearly we have that pi phi of 1 applied to any vector psi b. This was just going to be psi b, as we discovered above, because we're just multiplying psi b by 1. So by continuity, we see that and density of these psi b's, we see that this has got to be the identity on our Hilbert space. And from there, the result is fairly straightforward. So this is just which we have just shown is exactly phi of 1a, which, since phi is a state, is exactly, 1. And that's all we had to prove there. Pi u psi give the same state. Let me think. So you want to say if u in, yeah, will it give the same? Let's see. I think you won't get the exact same vector. You will get but will you get the same state? I don't think so, because if you had, maybe if you had them on both sides, the pi phi a on both sides, then you would be multiplying by u a u star, and that should give you the thing. But otherwise, I think you'll get something slightly different, because you would get, this is going to be equal to pi u a, I guess, which is not quite the same. But let's continue. I think maybe the next, so I'm about to talk about unitary equivalence of representations, and hopefully this will clear things up a little bit. So in fact, I mean, usually in C-star algebra theory, for things like representations or maps, or even to some extent positive elements, say, you often only care about things up to unitary equivalence. And what does that mean? Well, I will tell you what it means, at least in the case of representations. So just first of all, recall that a unitary transformation between two Hilbert spaces is just a bounded linear operator well, bounded comes for free in this case, but okay, just the point is that it's in B of H1, H2. So we want that U psi 1, U psi 2, that's in H2. This should be the same as psi 1, psi 2, inner product in H1. And note that if H1 is equal to H2, then of course U is in the C-star algebra B of H1, and then U is just a unitary in the sense that we saw earlier. So indeed, this is of course why unitary elements are called unitaries. Now we know that we can always represent our C-star algebra on a Hilbert space. So in fact, unitary elements in this C-star algebra are in fact unitary operators. Well, that's a little bit of a lie. Maybe it's not one B of H, maybe it's some projection. And the projection is your unit in your C-star algebra, but okay. I suppose, yeah, given the universal representation, that should always be true, that you get 1H. Okay, so definition. So let A be a C-star algebra, and we're going to take two representations of A. And we say that they're unitary equivalent. If we have some unitary, and this should intertwine the representations in the sense that applying U pi 1A U star, this should give us pi 2 of A for every A and A. So it doesn't take a lot of work to show that this is indeed an yeah, sure. It should be or invertible linear operators say. You could also say that. Okay, so you can, a moment's thought, you get that this is a unitary equivalence is indeed an equivalence relation on the representations of a C-star algebra. So that's not so hard to show. Okay, so now let's talk about cyclic representations and unitary equivalence. So this will be a cyclic representation with cyclic vector psi. And let's take another cyclic representation. With cyclic vector mu, then we have the following equivalences. So first, these are unitary equivalent. And the unitary that implements this equivalence sends psi to mu. And this is equivalent So yes, I guess this should answer your question, Yannick, maybe about whether we get the same state. Seems that we probably do, in fact, in this setting. Okay. Okay, if one holds, we have this unitary mapping psi to mu. And this is a unitary, so this note also implies that psi is going to be the same as u star mu. So just multiplying u star on either side. So we want to show this is the same as pi to a mu inner product mu. Well, whoops, that should be a u, not a mu. I did some bad choice of notation here, u and mu. Okay, so we can move this u star over to the other side. And now we're in H2. And this here is pi 2 just by definition of the unitary equivalence. So that was pretty easy. Okay, so this shows 1 implies 2. So now let's suppose that 2 holds. So that is that pi 1 a psi inner product psi in H1 is the same as, oops. So we want to define u from pi 1a psi to pi 2a mu in the obvious way. So we're going to map pi 1a psi to pi 2a mu. And it's easy to see that this is at least a linear map. We would like to know that it's bounded so that we can extend it to H1 and H2. So we see that u pi 1 a psi So that's just by how we defined u. And that's the same as pi 2 b star a mu H2, just moving the pi 2b operator pi 2b across and then using the fact that this is a representation. And then again, by definition, by our assumption here that pi 1a psi is pi 2a mu, we see that this is the same as pi 1 b a star psi in H1. And then we can just move our b back across. So in particular, if we put an a in the second coordinate, then we get that this holds for every A and A, and this is a cyclic vector. So guys of this form are dense in, well, okay, I mean, this is how we've defined it on pi 1 AXI, and these guys are dense. So that means that this U is bounded on pi 1 AXI, and we can extend it to H1 to H2. Which we'll just also call U. And it's clear by this computation here, and by the fact that this is evidently a surjective map, that indeed this will be a unitary. Okay, so we need to show that this unitary is actually a unitary equivalence of the representations, and that it maps psi to mu. So take some element A and A, and then we see that for every B and A, we have so U pi 1A, we're going to apply this to pi 1B psi to say something about this U pi 1A. So this is an arbitrary vector in our vector space up to epsilon, whatever. Now rearranging things and using the fact that pi 1 is representation, we have this is U pi 1A psi, which now by definition of our map U is pi 1 AB mu. And oops, sorry, pi 2. And then we can just take this apart now. So we get pi 2A, pi 2B mu, and pi 2B mu is just by definition of U of pi 1B psi. And now we can move the U over, and we get pi 2A U. And again, since pi 1B, these elements here are dense in our Hilbert space H1, we get that U pi 1A equals pi 2. Pi 2AU, since U is a unitary, this implies that conjugation by this unitary of pi 1 of A is pi 2 of A, and that's for every A and A. So indeed, this is unitary equivalence. Okay, so it remains to show that this map indeed maps psi to mu, but okay, that's not so difficult. So we just take an approximate unit. Well, we know that u pi 1, u lambda of psi is just going to be, by definition of u, pi 2 u lambda of mu. So taking the limit, we see that we get u psi equals mu as we wanted. So yeah, up to unitary equivalence. You can see that unitary equivalence really means that these are essentially the same representations. Okay, we also have the notion of a non-degenerate representation. I don't know why my pen goes crazy like that sometimes, sorry. So it's non-degenerate if the linear span of pi a applied to vectors in H, which we will denote pi a H, is dense. So if we think about this, we could have equivalently said that for every non-zero vector in our Hilbert space, we can find some non-zero element A in our C-star algebra such that pi a of psi is non-zero. Okay, so it's clear that our cyclic representations are going to be non-degenerate, but it's not necessarily the case that everything non-degenerate is cyclic. However, it turns out that anything non-degenerate will be a direct sum of cyclic representations. I guess I should say direct sum there. Okay, so non-degenerate and cyclics are sort of the components of a non-degenerate representation. Okay, so how are we going to find a cyclic representation that's at least a direct summand in H pi? Well, just take some psi in H, non-zero vector, and we can look at the subspace of H that is generated by the orbit of psi under the representation. So by that, I just mean that we take psi A, apply it to phi, take the closed linear span of such guys. Okay, so by Zorn's lemma, we can find a maximal set such that these H psi's will be pairwise orthogonal. Okay, so we can define a sort of sub-representation in an obvious way by just restricting and then it's clear that these guys will be cyclic representations. And since these H psi's are by assumption pairwise orthogonal, that means that their direct sum is a Hilbert space inside of H. Okay, so what we would like is that this is all of H. So suppose we have some eta in H. If anyone out there has a tip about how to make that stop happening on my iPad, I'd be very much appreciated. So let's take some vector in the orthogonal complement. And since it's in the orthogonal complement of all these h xi's, then we can again form this h eta. And since eta is in the orthogonal complement, you can see that the inner product of any element in h psi for psi and s will be 0. Excuse me, which is to say that eta is orthogonal to all these h psi's. So for all of a pi a psi, it's mapped into h psi. So by maximality of our set X, we got to have that pi a eta is 0. And that's for every a and a. In particular, this is true for even non-zero a. By assumption, pi is non-degenerate. So that means that we must have that pi a is 0, right? Oh, we just decided that we were saying for all a, which means that eta itself is equal to 0, which means that there's nothing but the 0 vector in the orthogonal complement. So this is in fact everything. And we see that sorry. Okay. I seem to have misplaced a page. Ah, there we go. Okay, so there's actually quite a lot more that can be said about representations, but for the sake of eventually getting to Tristan's portion of the course, that's all I will say for now. I'm sure things might come up in the meantime, which we'll talk about. So I actually want to move on to the next topic in the syllabus, which is tensor products. And I probably won't quite finish that today. So I'll either finish saying something about tensor products next time, or perhaps Tristan will just take over and finish that off. But in any case, let us talk about tensor products of C-star algebras. So it's kind of hard to get particularly far in C-star algebra theory without having to take tensor products. I assume probably most of you are more or less familiar with tensor products of vector spaces, but let me just quickly recall what that is. So in particular, its universal property, because that will be invoked from time to time. So tensor product of two vector spaces E and W is itself a vector space. Which we denote V tensor W, which comes equipped with a bilinear map. Sending something of the form VW to an element which we denote by V tensor W. And it has the universal property that for any bilinear map, into a vector space Z, there exists a unique linear map from the tensor product of V and W, also into Z, such that F applied to elements V and W is the same as applying our bilinear map here and then taking this linear map. So that's just saying that we get this commutative diagram. where this tensor product is just this bilinear form I mentioned before. Here we have f to z, and then we get this map phi. Okay, so we want to be able to take the tensor product of two C-star algebras. Certainly we know we can do this by thinking of the C-star algebras as vector spaces. And in fact, it's not so difficult to decide how you should make multiplication and the involution work on the tensor product to make it into a star algebra. But it's a little bit delicate to make it into a C-star algebra because putting a norm on the tensor product turns out to be a tricky matter. And in fact, there's no unique way of doing this. So one in general often, or usually will have many, many different norms you can put on the tensor product of two C-star algebras. And the one we will hopefully, we won't quite get to today, but I'll set up at least, is called the spatial tensor product, or more often, probably these days, the minimal tensor product. But we won't really understand why it's called the minimal tensor product today. However, the fact that it's a spatial tensor product will be clear. The reason is that we're going to take the tensor product of two Hilbert spaces and represent our C-star algebras on this tensor product. So that's what's meant by spatial. So let H and K be two Hilbert spaces. Again, we know we can take the vector space tensor product. There's a question in the chat. Maybe Tristan can answer that. Let HK be Hilbert spaces. And H tensor K, their tensor product is vector spaces. So maybe it's just, before I do this, actually useful to mention, just in case you haven't seen tensor products before, that you can also think of V tensor W as just being generated by these guys, V tensor W. So you take the linear span of such guys. And then you mod out by relations of the form the tensor, let's see, lambda W1 plus W2 minus the tensor W1 minus lambda V, oh, we don't need a lambda there. V tensor W2. And then same thing with the linearity in the first component. Sorry, I kind of ran out of space. Hopefully that's ringing a bell in your linear algebra years. Okay, this is their algebraic, their vector space tensor product. We want to know how to put a norm on this to make it into a Hilbert space. So we can define an inner product on H tensor X, sorry, H tensor K, and it should satisfy the following. So if we look at these simple tensors, and we want to know what is this inner product, well, it's just the inner product of the size in H times the inner product of the etas in K. So to prove this, we're going to need this universal property of the tensor product that I just mentioned. So first we'll begin with an observation. So if we have two conjugate linear functionals, and we'll denote by phi bar and psi bar, they're complex conjugates. Which will then be linear functionals. And define phi bar tensor psi bar from H cross K into C by just taking the obvious thing. So this will be multiplying these two guys together. Then since phi bar and psi bar are linear, it's easy to, and multiplication is bilinear, we get that this map here is a bilinear map. So we can extend it to a linear map on the tensor product of H tensor K. Which I will also denote by phi bar tensor psi bar. And again, if we then just take the complex conjugate page. No. Okay. And we can then get a conjugate linear map by taking the complex conjugate, and I will call this phi tensor psi. Okay, so we're going to use this observation to construct our inner product. So for any psi in H, we can define phi psi to be the map that takes psi prime to psi psi prime. And similarly, for any eta in K, we can define psi eta on eta prime to be eta prime inner product in K. Then these are conjugate linear maps, since our inner products are assumed to be conjugate Oh, wait a second. Maybe I would have preferred if they weren't actually. I prefer their conjugate linear in the first variable, actually. Oof, how embarrassing. Okay, different conventions in different books, by the way. I will accidentally assume they're conjugate linear in the first, so I will change my notes so that this is the case. Anyway, so these are conjugate linear. And so we can define their tensor product, which I will denote by phi psi tensor eta, and apply this to element in the tensor product. And by the definition here of what these look like, well, we get that this is going to be that's in H tensor K. And since these simple tensors span our vector space, this will be true for all elements in H tensor K. Well, we'll get the sum of these things. Okay. So now let V be the vector space of conjugate linear maps from the tensor product into the complex numbers. Then we can define a map from H cross K into V, which takes psi eta to phi psi tensor eta, which we just saw as a nice conjugate linear map. And by the definition of psi phi psi eta, you can see that this will be a bilinear map. And so it extends to the tensor product. Linear map. In fact, uniquely, because we did have this question of uniqueness. Which I will call big phi. And then you want to set zeta prime to be phi of zeta. Wait a second. Sorry. So one can check relatively straightforward that this will give you a sesquilinear form. I'm running out of time, so I will leave the details to you. And by construction, it will satisfy this relation on simple tensors that we wanted. Okay, so what we need to do is check that it's, in fact, gives us an inner product. So the fact that it will satisfy complex conjugate of this is swapping well, I guess we want this for everybody in there, not just these simple tensors, but it will follow very easily. So it follows from this, together with the fact that any set zeta can be written as the linear sum of these simple tensors, so finite linear combination of those simple tensors. So really the difficult thing is checking that it is positive definite. Okay, so in the 2 minutes remaining, I'll probably do that and then I better end. So let's take some new in H tensor K. Then it's in the vector space tensor product, so we can write it as a finite sum of some psi j's tensor A to J, where xi j is in H, A to J is in K. Now let mu1 up to mu_m be an orthonormal basis for K. And in fact, really, we just need it for the span of these A to J's. Then we can write every A to J as some of these basis elements, and then upon potentially replacing our chi j's, we get that we can write mu as some new m, perhaps. And now we can look at the sesquilinear form applied to nu. Well, it's sesquilinear, so that gives us oops, should be an eta. Mu j tensor. Doing. Okay, and now we know what these inner products are by definition. Or sorry, we don't know that they're inner products yet, but we know that they decompose like this. And we know that these guys were chosen to be orthonormal, which means that this is now just and that is, of course, just the sum of the norms of these guys squared. Now, each of these are greater than 0. So, of course, this had better be greater than 0. And furthermore, if this happened to be equal to 0, then this is the sum of positive guys. So we need that each of these psi j's is equal to 0. Hence, each of the psi j's themselves are equal to 0. So mu was equal to 0. So indeed, it is positive definite. So we have an inner product. Okay, let me just end quickly with a definition. So sort of the obvious definition, H and K are Hilbert spaces. Then they're Hilbert space tensor product, which I will denote as H with a little hat on the tensor product, H tensor K, is defined to be the vector space tensor product closed with respect to this, the norm induced by this inner product. And a useful observation, which we will use, is that the norm of such a simple tensor is just the norm in H of psi and the norm K of eta. And we see that using this Hilbert space, we can now make sense of the tensor product of two operators on a Hilbert space, giving us another bounded operator on a Hilbert space. And that will allow us to construct the spatial norm, but that will have to wait till next time since I'm already over time. So apologies for that. And see you next Tuesday.